Imagine driving beneath the ocean floor, millions of tons of seawater pressing above you, while beneath your car lies a seamless fusion of concrete and steel assembled with near microscopic precision. It sounds like a scene from a science fiction movie, yet it's a real triumph of modern engineering. The underwater tunnel. But how did humans manage to construct such colossal structures amid crushing water pressure, unstable sediments, and an environment completely isolated from the surface? In this documentary,
Datascope takes you beneath the waves to uncover how humanity has turned the impossible into reality, creating breathtaking marvels hidden deep beneath the sea.
In today's world, underwater tunnels play a crucial role in expanding human connectivity and reshaping global infrastructure. These monumental structures unite lands once divided by vast oceans, mighty rivers, or deep bays, sparking a revolution in transportation and logistics. Imagine traveling from one island to another, or crossing a wide bay in just minutes, without ferries or towering bridges, all made possible by underwater tunnels. Beyond saving time, they sustain the global flow of goods and people, ensuring trade moves swiftly, safely, and efficiently. For many nations, underwater tunnels have become vital arteries of economic and industrial growth, especially for port cities, while unlocking new opportunities for global commerce and regional development. Building an underwater tunnel demands exhaustive preparation and near-perfect design precision, with every step calculated in detail to guarantee both feasibility and safety for the entire project. The first phase begins with comprehensive seabed surveys. Engineers study subsea topography, collect soil samples, and analyze rock strata to determine the geological structure, the bearing stability of the seabed, and any latent hazards that could affect construction. Alongside the technical work, environmental considerations are prioritized throughout planning and design. The project team must assess the tunnel's potential impacts on marine ecosystems, ensuring species are protected and natural habitats are disturbed as little as possible. To achieve this, they implement noise mitigation measures during construction and may even install artificial reef structures to create new habitats for marine life. After the survey is completed, the construction step begins. The immersed tube method is one of the most widely used techniques for constructing underwater tunnels. The process begins with the prefabrication of massive reinforced concrete segments on land. Each standard element measures approximately 217 meters in length and weighs over 73,000 tons. These segments are manufactured with extreme precision to ensure perfect alignment and watertight sealing once submerged. Inside each segment, several compartments are designed for specific functions. 2 main chambers for highway lanes, 1 for a railway line, and another service corridor dedicated to future maintenance and inspection. Once the sections are complete, they are transported to sea and carefully lowered into pre-dredged positions on the seabed using floating pontoons and specialized cranes. Each segment is then joined sequentially to form a continuous tunnel of the required length. The most critical phase of this method lies in the joint connections. If the seals are not handled with precision, seawater infiltration could pose serious risks. To prevent this, rubber gaskets are inserted between segments to ensure watertightness, while layers of sand and gravel are placed above and around the tunnel to prevent buoyancy caused by water pressure. Only after the connections are securely locked and stabilized are the temporary end bulkheads removed, transforming the individual tubes into a seamless, watertight tunnel. However, this technique is only suitable for areas with a stable seabed and gentle water currents. In environments with strong turbulence or complex underwater terrain, the immersed tube method becomes impractical due to difficulties in anchoring and maintaining waterproof integrity. Besides using the underground pipe lowering method, they also use the shield digging method to dig tunnels. The shield tunneling method, also known as tunnel boring machine, represents the most advanced technology in modern tunnel construction. A TBM operates as a colossal self-contained system capable of excavating soil, collecting debris, and installing reinforced concrete tunnel linings simultaneously in a continuous, closed-loop process. This technique enables uninterrupted excavation beneath the ground or riverbeds while maintaining precision, safety, and minimal environmental disturbance. At the front of the TBM lies a massive cutter head, nearly 12 meters in diameter and weighing over 200 tons. It is equipped with 140 high-strength steel cutting discs and blades rotating at approximately 2.7 revolutions per minute. As it spins, the cutter head exerts pressure up to 400 bar, enough to crush compact rock and soil. The excavated material is immediately drawn into the chamber behind the cutter head, where foam and water are injected to maintain earth pressure balance, an essential factor preventing collapse in soft or water-saturated ground. The slurry mixture is carried away on a continuous conveyor belt to the surface, where it passes through a discharge tower, mixed with lime to reduce moisture, and loaded onto trucks for disposal. Meanwhile, as excavation progresses, the TBM's rear section automatically installs precast concrete segments to form the tunnel lining. Once a full ring is completed, a grout injection system fills the gap between the lining and surrounding soil, securing the structure and ensuring it remains watertight. Afterward, hydraulic cylinders at the rear of the TBM push the entire machine forward, beginning the next cycle of excavate, install, advance. Each cycle takes roughly 90 minutes, producing 8 to 10 lining rings per day, equivalent to about 20 meters of finished tunnel. Operating around the clock, hundreds of engineers monitor pressure, temperature, power systems, and real-time camera feeds to maintain stability. Thanks to its sealed and automated design, the TBM can operate for months underground without interruption, symbolizing the pinnacle of modern tunnel engineering. However, its only major limitation is speed. When encountering extremely hard rock or irregular pressure zones, engineers must extract the machine and switch to alternative methods to continue construction safely. Next up is another method for constructing underground pipelines, the drill and blast method. In areas with hard geological formations, or where tunnel boring machines, TBMs, cannot operate effectively, engineers must revert to the drill and blast method, a traditional yet still widely used technique in underground construction. Unlike the continuous operation of TBMs, this method proceeds in sequential cycles of drilling, blasting, mucking, supporting, reinforcing, demanding high precision and strict adherence to safety protocols. The process begins with dozens of blast holes drilled into the tunnel face according to technical blueprints. Explosives in cartridge form are inserted deep into each borehole, fitted with electric detonators and connected by detonating cords arranged in groups to control the firing sequence. Each detonator is timed to optimize rock fragmentation while minimizing vibration and structural impact on the surface above. All explosive materials are scanned, tested, and certified safe before being brought underground. During preparation, ventilation fans and air ducts are disconnected and depressurized to prevent shockwave pressure from dislodging ventilation pipes. Before detonation, crews measure circuit resistance and thoroughly inspect all connections. Blasting only begins once every safety condition is verified. When the command is issued, electrical signals trigger the detonators, breaking approximately 1.5 meters of rock at the tunnel face. After each blast, work halts for at least 20 minutes to allow inspection and ventilation. On average, each blast consumes between 80 and 100 kilograms of explosives, with 9 to 18 blasts conducted daily depending on geology and project scale. Although this method offers faster progress and lower costs, it produces intense vibrations that can crack structures and cause water leakage, making it unsuitable for underwater tunnels. Additionally, shockwaves can severely impact marine life, so the drill and blast technique is primarily reserved for mountain tunnels or dry ground excavation, where TBM and immersed tube methods are impractical. When all three methods above fail, the last choice is traditional tunneling. When geological conditions or high water pressure make the use of TBMs or immersed tube methods impossible, engineers turn to the traditional excavation method. The process begins with the construction of a main vertical shaft, extending from the surface down to the tunnel level. This shaft serves as the lifeline of the entire project, used for transporting workers, machinery, materials, and excavated debris in and out of the site. The extracted soil and rock are drilled, loaded into sealed containers, and hoisted to the surface by cranes for further processing. In areas where blasting is prohibited or the soil is too weak, crews switch to hydraulic cutting tools to slice through sediment layers. Although this technique is slower, it significantly reduces the risk of ground settlement and ensures tunnel stability. After each excavation phase, the newly exposed section is immediately reinforced with shotcrete, followed by the installation of steel arches, mesh reinforcements, rock bolts, and anchors to prevent collapse and stabilize the structure. Mechanical and maintenance teams operate around the clock, monitoring air pressure, equipment integrity, and dewatering systems. Maintaining pressure equilibrium between the tunnel interior and the surrounding environment is the most critical factor. Any imbalance could allow seawater to infiltrate, flooding entire sections of the tunnel. By combining classical engineering principles with modern monitoring technologies, the traditional excavation method remains a reliable solution for underwater tunnel projects in complex geological settings, where only persistence, precision, and deep understanding of marine pressure can ensure the structure's safety beneath the ocean floor. After construction is completed, the next crucial phase is safety inspection and operational assessment. In many modern projects, both submerged and underground tunnels are designed with two levels, effectively doubling traffic capacity without expanding the structural footprint. Drivers can maintain a stable speed of about 60 kilometers per hour, while emergency exits are positioned every 200 meters. Once the structure is fully completed, engineers carry out a series of rigorous tests, including waterproofing integrity, pressure resistance, fire safety, heating and ventilation performance, and overall structural stability. However, the journey of an underwater tunnel doesn't end once it opens. Maintenance is what truly determines its longevity and safety. Dedicated technical teams conduct regular inspections of the concrete lining, waterproof membranes, support frames, and drainage systems to ensure no deformation or cracking occurs over time. Hundreds of sensors installed along the tunnel continuously monitor pressure, temperature, humidity, and vibration, transmitting real-time data to a central control room, where engineers can detect even the earliest signs of structural fatigue. In parallel, cleaning and sediment removal are carried out periodically using specialized vehicles equipped with high-pressure water jets and suction systems to keep the tunnel floor clear and prevent blockages. Through the combination of advanced sensor technology and precise manual maintenance routines, today's underwater tunnels can operate safely, efficiently, and sustainably for decades, enduring the harsh environment of the ocean depths while remaining a testament to human engineering resilience. Beneath the surface of the water, where sunlight rarely reaches, humanity has built pathways of steel and intelligence. Every meter of these tunnels is more than an engineering achievement. It's a symbol of courage and the relentless drive to surpass limits. And if you want to keep exploring how technology and human innovation are transforming our world every single day, make sure to like this video and subscribe to Mandarin Tech, where technology isn't just introduced, but told as a story of evolution shaping the future.